So we'll start it.
Yeah, you may start.
Okay. So very good afternoon to all of you. And today we have Professor Stefano Liberati from 𝗙𝗵𝗄. Stefano is also associated with the IFPU Institute, which is just beside ICTP. So Stefano recently has been working on various regular black hole candidates as well as black hole mimickers. So he will tell us today more about these interesting objects. So Stefano, it's up to you.
Thank you. Thanks you all for coming today, and thanks to the organizer for inviting me. So what I'm going to talk about today is regular black holes and black hole mimickers. And in doing that, I will try to highlight what is the status of research on that side, at least. And I think also some of the open issues that are emerging, not only in context of testing these ideas, but also in the context of making them fully consistent. So let me try to start from the very principle. So when we talk about black holes nowadays are a kind of reality. We talk about black holes because we have seen them in the sky. We have seen objects that fit all the requirements that we normally have when we want to discuss black holes. And at the same time, however, they are problematic objects, and they are problematic mainly beyond the horizon. So why they are problematic? They are problematic because they entail two features, at least the solution of general relativity associated to black holes, that are in a certain sense undesirable. One is singularities. And the singularities, as we know, are basically missing point from space-time, are point where general relativity ceases to be predictive and somehow require some better theory to describe what is going on in there. And also they have a Cauchy horizon, quite generically, in the sense that it's enough to have a rotating black hole to have a Cauchy horizon. A Cauchy horizon, which is nothing else than the inner horizon of a stationary black hole, is a very dangerous structure because basically marks the end of predictability. From the point of view of mathematical physics, for example, many people would tell you that you are not allowed to discuss anything beyond a Cauchy horizon because basically you do not have a unique extension. We normally do that because we trust the solution, whatever it tells us, beyond Cauchy horizons. But in a sense, that is far from being, clear. Normally, the idea is that quantum gravity should cure this undesirable feature. And in which sense it would cure this feature? Most of the people would think that when you go back to the singularity theorems, basically they will avoid the deformation of the singularity. So in order to be systematic and in a certain sense quantum gravity agnostic, let me step back and let's go back to square one, basically to Pero's singularity theorem. Pero's singularity theorem in 1965 basically works in two steps. The first steps is basically proving that given some reasonable assumption, the assumption are that the theory of gravity is general relativity plus the null energy condition, or if you want, it's enough to impose the null convergence condition, that the contraction of the Ricci tensor twice with any null vector would be greater than or equal to 0. Then you assume that the collapse generates a trapped surface. And then basically assuming all this stuff, you can basically deduce that a singularity will form, a focusing point will form in the future. A focusing point is a point where the expansion for the outgoing and outcongruence will go to minus infinity. The second part of the theorem is proving by a topological argument that this point cannot be a part of space-time, or the space-time cannot be globally hyperbolic. That means that somewhere there must be a Cauchy horizon. That is the alternative. What we can do in an agnostic way is to say, okay, let me assume that there is no focusing point, that something intervenes. That means, for example, that the general relativity received a correction. All in all, we often think of general relativity as a low energy effective field theory. And it's very natural to think that quantum correction will lead to an effective action, which still allows to define, a continuous geometry, but that will entail additional effects. Very often, approaches from quantum gravity describe basically the resolution of the singularity exactly in this way. For example, loop quantum cosmology, the equation, you can arrive at a modified Freeman equation that gave you a in the primordial universe, but this equation could also be derived from some f of r theories of gravity. So the idea is generally that you have some effective field theory of gravity that save the day. So you're basically renouncing to the idea that GR is all the way correct in describing the space-time, even close to the singularity formation. So now let's assume that something defocus the outgoing null congruence. What can happen? Basically, you can systematically describe the possibility for the defocusing. You can have the defocusing happens at a finite distance, or it happens at an infinite affine distance, so that means asymptotically defocus, or it doesn't defocus at all, but defocusing only up at infinity. This last case, you can prove that the ongoing congruence is still having a focusing point, a singular focusing point, and then you can basically rule it out. So at this point, you can ask yourself, what is the ongoing null congruence doing, the one that is pointing in this direction doing? You can have, again, the case in which it doesn't change sign, the expansion remains negative. Normally, the expansion for the ongoing congruence is negative, even here. Or it changes sign. So you can have, focusing or the focusing at finite distance or infinite distance, and with some radius which is corresponding to the radius at this fine distance or an infinite distance. And then you can check what is doing the ingoing null congruence there, if the expansion is changing sign or is not changing sign or is changing sign. So you have, in principle, 4 cases. Let's see them, what they are saying. The first case is is the one of evanescent horizons. Basically, what is telling you these cases is that you will have a geometry that describe an outer horizon, an inner horizon, and then a regular core. If you can have multiple copies of this kind of trapped region. Actually, you can have a trapped region, a pair of a trapped region, and an anti-trapped region. In principle, many of them in a row. An alternative is that you have the case in which you have at the finite affine distance, theta plus the outgoing congruence expansion change sign, but also the ingoing one change sign. This is basically what normally happens at a wormhole trout, but here it will happen at a space-like trout. Sometimes these are called hidden wormholes for this reason. So you go directly from a trapped region to an anti-trapped region in the future. You have a minimum radius, basically. Of course, to see the collapse version of this is not easy. You can do it at the cost, basically, of having maybe 2 unknown analytical points. Unfortunately, here there is a mistake. The line should be here. But anyway, you have then a pair of anti-trap and trapped region. I just want to stress that you can see this situation as the limit in which this deformation, these are line of constant radius. Basically, you have one that becomes this one. And then you basically avoid the inner horizon here. You have a past inner horizon here, a past inner horizon here, and a past outer horizon here. Basically, you cut that, you cut this, and then you glue this one. So the case of the hidden wormholes can be seen as a kind of limit case of the evanescent horizon one. And then you have the asymptotic resolution of the singularity, but these are asymptotic, and in a certain sense, to me, they look like physical, and I will not discuss them in what follows. Basically, I will focus on the first 2 cases. By the way, the same analysis on the resolution of singularity, the same systematic analysis can be done also for the Big Bang. And there you can see that there are only 3 possibilities for the resolution of the initial singularity. Let's move on because the thing is even more interesting than that, because you can ask yourself, what happens if the focusing happens before you basically form a trapped region, you have an horizon? Well, in that case, you can have horizonless objects. And then this would be basically black hole mimickers in one case, because there will be, in the category 1 case, you get basically a kind of ultra-compact star. And in the case of the hidden wormhole, instead, you have basically a traversable wormhole. You can see it. We will see it better in what follows. Let me say that when you have a sufficiently compact object and you don't have horizon, if you have the usual unstable light ring, that for those of you not familiar, for example, with the black hole shadow, is basically this unstable light ring, in 𝗙𝗏𝗃 is at 3M, is what is mainly determining the size of the black hole shadow we see with the Event Horizon Telescope. And there is an interesting theorem that tells you that if you have an object that is sufficiently compact to have an unstable light ring, it will also have a stable light ring further inside. And so this ultra-compact object generically have two light rings and a stable one close to the object, or even where the object is. And this is a potential source of instability, because if you have a stable light ring, massless stuff can accumulate there. We will see more about this later on. So let me summarize. Basically, the systematic analysis of the resolution of singularities brings you up with basically with two possibilities. With this, it would be the general structure, for example, of a GR black hole, a spherically symmetric GR black hole like Schwarzschild, okay? Here you would have instead the regular black hole would be having an unstable light ring, an outer horizon and an inner horizon, or instead of an inner horizon, a wormhole throat, which on the other side has an anti-trapped region. In the case of you can have also the case in which you have no horizons, and then you have a surface, you have a stable light ring, a stable light ring, or a wormhole throat. Okay, so this is the general structure, but in reality now, if we want to analyze better things, we need to start modeling them with some global geometry. I've done only local analysis so far. So let's...
Sudipta here. So all these spacetimes will violate some kind of energy condition, right?
Yes, I will go to basically which spacetime violates which energy condition later on, if it's okay for you. I can describe this more in detail.
Okay, sure.
Okay, so let's go for the metrics now. Now I am trying to introduce some stationary metrics that basically give flesh to this local resolution of the singularity that I've described. Let's go start with class 1. So the class in which the expansion for the outgoing congruence change sign somewhere, the focus, but the ingoing congruence keep focusing. It keeps having theta negative. And what this class of metrics are the ones that are more familiar to people, because are the so-called regular black hole metrics. There have been several proposals in the literature. The earliest one is Bardeen 1, 1968. And they are all basically doing the same things. What they are doing is asymptotically, they're giving you the IDM mass. Basically, you replace here the IDM mass with some Misner-Sharp mass that depends on space, given that we want to have static metrics because they're statically symmetric. You don't want time dependence. You can complicate things with time dependence, but let's stick for that for the moment to this. And then what you can do is that you want at infinity to recover the IDM mass. And locally, you can check that if the Kretschmann scalar, which is enough to check in a spherically symmetric metric, if the curvature are all regular, you want the Kretschmann scalar to be regular at r equals 0. All you need is that 𝗕𝗏𝗃 goes like at least as r cube close to r equals 0. They do all the same trick, basically, here you can check. And this solution, of course, once you produce them, they are not anymore vacuum solution of general relativity. You can also produce rotating version of this solution by applying the Janice-Newman procedure. Also, although there will be stuff to be said about that, some care is to be required. But let's move on the spherical symmetric metric, because I want to show you the general structure of this solution. I mean, you have an effective stress energy tensor. You can think, I mean, you can insert this metric in GR and get an effective stress energy tensor. Of course, you can always interpret this effective stress energy tensor as the byproduct of the extra term with respect to Einstein-Hilbert in your effective action, okay? Now, the general structure that you get, this is the structure you get, for example, for the I-word regular black hole, is that most of these, all the solution I show you have an isotropic de Sitter core, basically P equal minus rho at the center. Then you have an inner horizon, an ergo region between the two horizons. That means a region where the Killing vector has is space-like, the DDT is space-like. Then you have an outer horizon, a region, a layer of matter, which is mildly anisotropic, and then you have another layer with a different, with more anisotropy, but still you can say there is matter outside, and then you rapidly decays in vacuum. Okay. Now let's see what happens if you can take always this regularization parameter and make it larger. And of course, the 1 minus 2m over r might have not anymore roots. Here you have normally for L sufficiently small, you have two roots, but it's easy to see that if it becomes too large, you have no roots. Then you have an horizonless object, as I anticipated. This object basically has a gigantic de Sitter core and a thin crust. So what is happening is, and now a pair of unstable and stable light ring. And you see, basically the structure is this, and this is common, it's not just I-word, it's basically common to all this, the model I listed before. You have, as you improve, increase the regularization parameter in units of the mass of the black hole, you get this is away from 𝗙𝗏𝗃, you see, and you get basically immediately an inner and outer horizon. And then you can get an extremal black hole here. And then beyond that, you don't have a naked singularity because it's non-singular. The solution, you have an ultra-compact object, what you may call a black hole mimicker. I call it a black hole mimicker because in a sense it has light rings, for example, it can mimic shadows. But if you get going, increasing the regularization parameter, the two light ring merge, and then you have a compact star which has no light ring. So, for example, you would expect that it wouldn't create the same kind of shadow we see in the Event Horizon Telescope. And let me also notice that the structure that we recover is very similar to the graph star one, for those that are familiar with that model. One comment I want to make is that, of course, you can immediately realize that when you ask that M goes like R cube for R small, it's easy to see that you're asking basically for your line element to go like the Sitter one, close to the... But it's not just the Sitter, not because you have 1 minus A R squared, but you can always you can construct solution where A is negative, and then you would not have the Sitter, but you would have an anti-de Sitter core. And the fact that most of these models I show you in the past were dealing with the Sitter core is just historic reasons. But in principle, you can easily build from the solution I show you with the Sitter core, solution which are almost identical with an anti-de Sitter core. So we recently investigated this branch of solution. And this branch of solution basically they are showing different behavior. For example, if you look at the quasi-normal modes, they are different. So, and if you go to the ultra-compact limit, their echoes will be different. So, in principle, it's interesting to see that changing the core, even in the black hole branch, would lead you to a different kind of ringing of the object. Let me just add that there is also a good reason to explore IDS core, because there are models where you show the effect of vacuum polarization in semi-classical gravity, how they can become important close to the Book-Wall limit for ultra-compact objects. And there they help you to go beyond the Book-Wall limit. And you can show that generically you got black hole mimickers with anti-de Sitter cores in that case. So we have also some, hint from semi-classical gravity pointing in this direction. Now, concerning the energy condition, that was Suvito was asking me. Basically, there are the thumb rule is the following. If you have a de Sitter core regular black hole, like the traditional one, they all violate the strong energy condition. And it's obvious because the strong energy condition is violated in the Sitter, right? But they do not violate the null energy condition. And they need to violate the strong energy condition basically only at the core. So the Sitter core is basically supporting the structure. And this, you may think that this is against the Lepper's theorem, where normally you use the null energy condition, but you have to think that these objects have an inner horizon. So when you want to apply a singularity theorem to them, you have in principle to appeal to the Hawking theorem. And the Lepper's theorem is a later theorem that applies also when you don't have a global hyperbolic spacetime. But there you require only the strong energy condition violation. And this is exactly what regular black hole with a Sitter core do. De Sitter core, in principle, doesn't violate the strong energy condition. However, in order to interpolate with an asymptotic flat spacetime and vacuum outside, you always see that there is locally some strong energy condition violation, between the core and the outer horizon. So, in a certain sense, you always have a strong energy condition violation also in this case. Concerning how you can get this solution from some theory, people has noticed long ago that this theory can be produced by suitable nonlinear electrodynamics added to GR. Now, if you have a nonlinear electrodynamics, but in a certain sense, it's a weak statement because you need a different nonlinear electrodynamic for different solutions. Other people has explored recently that in D greater than 4 dimension, you can have quasi-topological theories which are built out of curvature invariance, but which are in addition giving you only second order field equation when you specialize to spherically symmetric metrics. And also it was found, for example, the Auer solution as a solution of 4D Einstein-Hilbert plus biproca gravity. So there are some attempts in this direction. Of course, it's very difficult to imagine that at the moment without a guidance from a true quantum gravity or a model of, maybe in asymptotic safety, something that tells you that these Lagrangians that seem very ad hoc, very tuned, do not renormalize the energy, that there are something that keep their behavior the right one to get this solution. So there is still work to do in that direction. Now, let me try to stop for a moment commenting about this class 1, because in this class 1, you may object that I've considered static geometries, but this static geometry have inner horizon, which are also Cauchy horizon. And I started my analysis saying that they didn't want to have singularity, but neither Cauchy horizon, because they mark a breakdown of predictability. So the things that is interesting is that you immediately realize that having an inner horizon spells troubles, because an inner horizon, if it is stationary, leads to an infinite focusing of your outgoing light rays. This is the structure of the outgoing light rays, for example, in Kerr. And this is also corresponding to an infinite blue shift. If you take an observer here going from, toward A plus, and another observer falling toward the Cauchy horizon, you see that what this observer emits in an infinite time is reaching a fine parameter by a fine time or proper time, sorry, by this other time-like observer. So this observer sees an infinite blue shift close to the inner horizon, which if this is also Cauchy horizon. And this is a feature that is not just of regular black hole with inner horizon, of course, it's a feature also of Reisner-Nostrom black hole and Kerr black hole. Now, the infinite blue shift, this infinite focusing, is not obvious per se, telling you that there is a big problem. It's just a feature of the geometry. But you may wonder, does it lead to an unbound amplification of perturbation? And the answer is that yes, it does. And what it does is that you have a phenomenon, classical phenomenon, which is mass inflation. So in order to see that this infinite blue shift lead to a strong back reaction, you need to have something to which give energy. So normally, for example, one exercise you can do is to take an outgoing shell in this direction inside a black hole and an ingoing shell. And you take this shell closer and closer to the Cauchy horizon. And then you look at the energy at the crossing, and in particular, show that the mass, the Misner mass, after the crossing, so in the region IA, grows exponentially as you go very close to the Cauchy horizon. And you see it grows exponentially with a parameter which is the inner horizon surface gravity. Now, this makes sense, because this is exactly the exponential governing the infinite focusing at the inner horizon. So you can also refine the model having a continuous flux here and a shell still going in this direction. If you can explore the possibility to consider the possibility perturbation in a universe, an expanding universe, very rapidly. And then, in a certain sense, you may have a kind of damping of this exponential behavior, but this will happen only after a time v is the time on square minus, so it's the time marking this separation of these ingoing rays. Only after a time 1 over square root of lambda, and of course, if lambda is small, as in your universe, it will be too long to save you from an initial exponential amplification as determined if you put an input, for example, perturbation, which are power decaying like a power law, like in the price law. Similarly, also Hawking radiation could do the same effect, but again, Hawking radiation will become relevant too late for astrophysical black hole to save the day. So an open issue, of course, is that you can say, okay, but this is a phenomenon of Cauchy horizon. What if you go back to the previous picture where you have a dynamical inner horizon that never reaches Screen plus, so maybe you don't have a Cauchy horizon at all. The solution is not that easy because you can show that even if you don't have a Cauchy horizon, but you have a slowly evolving inner horizon, then a slowly evolving inner horizon will still accumulate exponentially fast energy, and that will basically bring you out of a regime where you can ignore back reaction very rapidly. So basically, you see, these are in units of the mass of your initial object, you immediately shoot out. And so you have to do, if you have an object that tries to become stationary, basically immediately you need to have an destabilization of the inner horizon. I want to stress that this conclusion is not, again, related to regular black hole. It's a generic conclusion. So even in a Kerr geometry, before the Kerr geometry becomes stationary, before you can talk about an event horizon, but you have also only an outer trapping horizon, which is still dynamical, you have that the horizon will start to mess up your geometry and try to generate a geometry which is not the Kerr geometry. So a few musing about this. I think that, you see, my initial analysis was to resolve the singularity, enforce the strong cosmic censorship. We tried to enforce stationary geometry on this picture, and we saw that this stationary geometry cannot be stationary, that somehow you needed to have a large back reaction effects from the presence of the inner horizon, even before the geometry becomes stationary. So it seems to corroborate the analysis that once you have a regular black hole, given that if they are regularized in this first +1 way, they don't have inner horizon. They don't want to have Cauchy horizon as well. Then you may say, okay, but there is another possibility to stabilize the inner horizon and make it stationary. It would be if the inner horizon stabilizes on a configuration that is at zero surface gravity, because in that case, that's exponential field. And you may wonder if there is the possibility to have black hole which have zero surface gravity at the inner horizon and not zero surface gravity at the outer horizon, so they can have still the thermodynamical property that we all love. And the possibility is there. You can build a solution, for example, which have multiple degenerate inner horizon and a standard outer horizon. And you can show that the mass inflation goes to zero in this case. However, sometimes nature is subtle because you have to worry also about semi-classical gravity. Normally, when we talk about astrophysical black hole, we don't worry about semi-classical gravity because we deal with the outer horizon. And outer horizon, let's say the standard law is that they can be in a regime where you can avoid to worry too much about the semi-classical effect. Although this is a standard law that not everybody share. Think about people that, for example, think about fuzzball and the idea that immediately behind the horizon, the geometry is completely different from what you would expect. But even without going so radical, you can immediately show that, for example, if you want to have an Uru state on your stationary geometry, the state that 𝗪 gave you the thermal flux associated with Hawking radiation, this Uru state cannot be regular on the Cauchy horizon. And it cannot be regular by a factor that basically is dominated by the difference between the two surface gravities. And this is a problem because even if you make a kappa minus equal to 0, you still will have a divergence at the inner horizon. So, of course, it has to be seen what happens in a dynamical situation, which is even more subtle. We're investigating, we are close to publish something concerning this. And it has to be seen what happens if you have a dynamical situation, a collapse, and furthermore, you produce kappa minus equal to 0. So that is still work in the making. Also,
Can I make a comment here? Or
yes.
yeah, so like in this paper by Hollands and Wald, so what they also show is that for three-dimensional BTZ black hole, there is actually no divergence at the Cauchy horizon. So, do you have a comment like what happens on the lower dimension and how you envisage these issues?
The problem is that, it is a 𝗕𝗔 rotating or not rotating, remind me.
Rotating BTZ
Okay,
black.
but you see, in the case of the 𝗕𝗔, when you have a rotating black hole, it's much more subtle, the story, no? Because you have also to decide what kind of vacuum you're setting. So, in principle, I guess that when you are in 3 dimensions, you have more freedom. It's more easy to find it's not impossible to find a regular vacuum. But I don't have a physical explanation why, in the special case of 𝗕𝗔, should be possible. But 𝗕𝗔, you now also have the cosmological constant. It may be that they are setting basically in the equivalent of a kind of thermal equilibrium thanks to the cosmological horizon. My conjecture is that there could be an interplay between the two horizons in that case. Here I'm strictly speaking about asymptotically flat situations. In this case, I would say that which are the situation which we are more worried about, because are the one we want to see if we can have 4D black hole which are stable, and asymptotic flatness, of course, is an abstraction, but you know what I mean, is that if you don't have asymptotic flat stable stationary solution, you still worry about if that is the endpoint of your collapse. So I think that in the case of a cosmological horizon, there could be a way to set up a kind of global thermal equilibrium, right? It's like the case in which you have 値-Hawking, in which you can have a state which is regular both of the black hole and white hole horizon of the eternal black hole. So maybe that there is something going on there.
So for example, the paper that is under preparation, as you mentioned, so that is for asymptotically flat scenario, right?
Yes, we are considering asymptotic flatness.
Okay, thanks.
So I just want to say that the semi-classical stability is an open issue. It seems to say that, yes, that Cauchy horizon are always in a sense problematic. Of course, if you have a collapse, you have a dynamical collapse and you form a trapped region that lasts for a finite amount of time, you don't have Cauchy horizon. And that is far from clear if you have an issue semi-classically with the inner horizon. And this is the point I want to make. Also, of course, you can make a black hole which are completely degenerate, where all the horizons are multiple degenerate, and these are basically zero temperature black hole. And we have conjectured that that could be called remnants because they would be super stable. They don't have any non-instability. But it has to be seen if they can be reached in a continuous way from any realistic astrophysical black hole. So anyway, the take-home message is that the regular black hole of the first class are most probably have to be described as dynamical objects. I want to put the stress on this, that somehow it's about time if we want to go in this game, and not only for regular black hole, because I think that many of the comments I made apply also to Kerr black hole. We need to understand better the evolving horizon and the stability of this evolving horizon. I want just to stress that there are also semi-classical numerical simulation now by Frolov and Boyanov, two separate papers that seem to find the same kind of behavior. They analyze the collapse in 2D, another paper in 3+1, but using basically the Polyakov approximation to promote the 2D calculation to 3+1. And basically what they find is similar to what I was showing you, a bounce. You say trapped region, untrapped region, anti-trapped region, and many of them possibly. So it looks like there is a lot to understand in the dynamics of this object, and that the dynamics is some kind of unavoidable step that we need to do in this day. In summary, I want to go back to that diagram to summarize what we understand now. So we have the inner horizon, which is plagued by mass inflation and semi-classical instability. We have the outer horizon, which is slowly evolving by Hawking radiation. Most probably, the trapped region is unstable more rapidly due to the inner horizon. You may have a point where of equilibrium at the extremality, but there, in external black hole horizon, independently if it's regular or not regular, is characterized by what is called the 𝗬𝗏 instability. Higher order radial derivatives of the field on the geometry that you can describe as the near horizon geometry seems to grow with the power law and to generate back reaction. There is a stream of papers by Stefanos Țăṛetakis on that. So it's still unclear if the extremal black hole can be an equilibrium point. If you go beyond and you imagine your regularization parameter due to this instability acquires a time dependence. So if you go beyond, basically you have a black hole mimicker with two light rings, but the stable light ring, as we say, could be a source of instability. We will see some red herring about that later on. So it's not clear where you have to sit in this diagram, if there is a preferred point. So we will see. I mean, this is an open issue. So let's move to the class 2. And a typical example of a stationary geometry for class 2 is the Simpson-Visser black bounce. So the recipe to build the Simpson-Visser black bounce, for example, for Schwarzschild, is to replace R with the square root of R squared plus R squared. You see that the error radius here, even for R equals 0, is finite as the value of L. And this is basically producing that structure that I was telling you about. You can generate a rotating counterpart with the Janice-Newman algorithm, and you can show that this solution generically interpolate between a space-like throat behind the outer horizon. If you increase the regularization parameter, you have a single solution which has a null throat sitting on. So basically, from outside, it looks to you like a black hole horizon, but in reality, it's a wormhole throat, a null wormhole throat, and you will get another universe on the other side, or another side of our universe. Or if you increase further L, you get basically an horizonless object which has a time-like throat, and this is the standard traversable universe. The diagram describing this solution is that you have for L smaller than 2m, basically you always have a black hole with an hidden throat. Then when you get 2m, you have the null throat. Then you have a time-like throat, which is also a stable light ring. And you have the unstable light ring here at 3m. And then when they meet, you have a wormhole with an unstable light ring at the wormhole throat. In this case, you have all these solutions do violate the null energy condition. And this is, in a certain sense, intuitive to see, because in this case, you don't have an inner horizon. So you have basically to overcome also the Penrose theorem. So you need the null energy condition violation. And this has been found that the Simpson-Visser metric as a solution of GR plus nonlinear electrodynamics and the Gauss scalar field A bit less is understood about other possibility in higher dimension and the way to find the solution, at least at the best of my knowledge. And it's still unclear if these solutions suffer from instabilities. By the way, there are also the solutions suggested, for example, in loop quantum gravity by Asteker and collaborators recently, where they think that at the end of the evaporation, basically you have the end up of your trapped region in a transition, which is described by quantum gravity, to an anti-trapped region. You can compare what is happening in these two situations. For example, you see here the study of the quasi-normal modes for a spin-2 times field between a Bardeen regular black hole and a Bardeen quasi-black hole, a Simpson-Visser black bounce, and a Simpson-Visser solution in the regime in which we have no horizon but just a wormhole. And basically, the upshot is that the Simpson-Visser black bounce, when the black hole configuration shows less deviation with respect to 𝗙𝗏𝗃 with respect, for example, to a Bardeen regular black hole. It's interesting enough, we did a kind of case study, and we showed that if you have third generation gravitational wave detectors, in principle, such detectors should be able to see deviation from the quasi-normal modes of 𝗙𝗏𝗃. In this case, we haven't done the rotating case. If L over M is order 10 to the minus 1. Now you may say, well, but L should be a Planck scale. Well, that is not so clear. First of all, due to the previous discussed stability, maybe that you end up, with an extreme linear horizon, and a core which is sufficiently large. Secondly, L can be some effective field theory scale, which is not just a combination of it could be a combination of a quantum gravity scale and other scale in the effective field theory. That we don't know. In any case, yes, of course, with third generation detector, you will see some deviation only if you have still a black hole, but with L over M over at least 10 to the minus 1. Quasi-black hole configuration, black hole mimickers configuration, have in the regime where they are just above forming an extremal black hole. That is interesting because you see that the imaginary part of the quasi-normal modes goes to 0. What it means? It means they do not decay fast, or almost, or they don't decay at all. Normally, this is a red herring, because if your quasi-normal modes at the linear level do not decay, or decay very slowly, you cannot be sure you can ignore the nonlinear effects. And nonlinear effects then will tell you that you may have a kind of nonlinear instability associated with the stable inner light ring. There are very few studies. To the best of my knowledge, basically, there is a study by the group of 𝗏𝗏𝗃 looking at boson star, which are much more dilute than the object that we are looking. And depending on the initial condition, they were getting or back a black hole due to this instability or something less dilute. But it's an open issue again. So definitely it would be needed a nonlinear analysis for the horizonless configuration. How to see these objects? If you have a horizonless configuration, there has been a strong search for equals. Basically, the main point is that even if you have an object which is very close to form an horizon, even for delta very small, you have a logarithm which the separation between the equals, what would be the equals? Would be the fact that if you have, for example, gravitational wave hitting the potential barrier, let's say around 3m, one part is reflected, one part is transmitted. Normally, it's lost into the horizon. But if you have a hard surface, it will bounce back, hit the potential barrier. One part is transmitted, one part is reflected, and you will have a series of echoes. The separation between these echoes is ruled by a logarithm of basically the compactness, how far you are from doing a black hole. So even if this number is a very small number, e to the minus something, the logarithm basically gives you something that could be observed. However, I think personally that this is a bit of a naive analysis, because first of all, there are no mirror at the surface of ultra-compact objects. These are not perfectly reflecting surface. If you think an ultra-compact object that somehow is stable, actually should be a very good absorber. When you throw something on it, it should use the energy of absorbed to expand and try to repristinate its standard compactness, which should be less than the compactness of a black hole, of course. So you won't expect that there is a perfectly reflecting surface. Whatever goes through this, the core of this object, you can show that, for example, in the semi-classical stars I was telling you about before, they have a very deep, high curvature region at the center. So what it happens that your wave has to go down a very deep potential well and climb up again in order to exit and hit again the potential barrier outside. But that could take millions of years. So it may even completely kill the echoes. Another point is that even if you have a reflecting, most of the rays are reflected. Then what you have is that incoming low densities becoming outgoing high densities, because you are basically close to form a black hole, you have a peeling structure. Outgoing and null rays will peel off very close to what they do, for example, around the 𝗏𝗏 black hole. This can send you low density and high density, and so generically you expect a lot of back reaction. And if you start to vary to object to be dynamical, you see that the pattern of the echoes that can still be there if the core is not shallow, is not too deep. If you have a shallow core where there is not too much curvature at the center, but still it would be different from the equidistant echoes that people now is searching actively, for example, in LIGO Virgo. Another, and I'm closing, basically observation that has been often claimed concerning black hole mimickers is the idea that with Event Horizon Telescope, for example, you can have an upper bound of how much luminosity can come back from an eventual surface replacing the horizon of Sagittarius A star. And the constraint goes in this way. Basically, you can estimate what is the minimum surface luminosity that you expect at infinity given a given accretion rate. And you have a parameter, basically, that is constrained by observation. And now you can link this parameter, if you suppose that the surface of the object is purely reflective, in a very simple way to the compactness. But again, this is something that is very idealized, doesn't take into account two things, that as the black hole mimicker is becoming closer and closer to form a black hole, the escaping angle on which stuff falling, light falling on the black hole can bounce, the black hole mimicker can bounce back, is closing with this law for mu very close to 0. And also, you have that in general, the object will have some absorption or even just an inelastic scattering. And you can basically simulate what is going on. We did a truthful analysis of this, and you can show that basically you lose the constraint, at least with current observation. You cannot cast a very strong constraint because basically you will have a lot of the light will bounce many times on the surface because a lot of light cannot escape immediately. Only the one that is bouncing back almost orthogonally to the surface escape. Not only, but a part of it is absorbed and is released over a long time in principle. And that basically doesn't allow you to cast a constraint the simple way. If you want more details, it's quite complicated. They are in this paper. And then I'm coming to the closure. So my message, what it is? My message is that the good news is that we can somehow catalog the kind of regular solution, regular spacetime that may replace a singular one without having too much detailed knowledge of quantum gravity. Although I'm not saying that this won't be necessary, but in a sense, there is a lot we can start saying waiting for a quantum gravity theory. What we have seen is that there are two main categories that are emerging when you regularize spherically symmetric black holes. You have a category where you have outer inner horizon de Sitter or anti-de Sitter core. You have another category which has where you basically go directly from a trapped region to an anti-trapped region, and you have what is called an hidden wormhole. These categories have a corresponding horizonless object, which we call black hole mimickers if they have light rings. These black hole mimickers can be grav star-like objects, so huge maximally symmetric cores and a thin layer of matter and then vacuum. Or you can have basically Lorentzian wormholes. All these objects, when you look at the quasi-normal modes, they show deviation from the quasi-normal modes that you would expect for the GR solution. The deviation, of course, are more marked in the horizontal case, less marked in the horizontal But there is, in general, in the category A, in the first category, the one with inner horizon, you have a series of instability that are strongly suggesting that this should be dynamical object, and that what we should understand is their typical lifetime, if a trapped region can last for a sufficiently long time to be compatible with observation. And because you see, it's not obvious if it will evaporate. For example, imagine you have an inner horizon instability. The inner horizon, the classical effects do not violate the energy condition. Mass inflation will try to push it inward. But semi-classical effect violate the energy condition, try to push the inner horizon outward. All the simulations are suggesting that the inner horizon goes outward, and that basically your trapped region will be shaped like a drop, and where it's killed by the stability of the inner horizon. But this instability, when the inner horizon starts to evolve rapidly, may be killed simply because you don't respect the adiabatic condition that in dynamical horizon ensure that you're still accumulating energy. So it may take a very long time for this trapped region to be destroyed. If it is going scale, I don't know, like mass square, then it can be a very long time compatible with astrophysical observation. Or alternatively, this trapped region may disappear and produce a series of bounces from trap to anti-trap and so on. And then maybe these are very rapid and they are hidden in what we call the ring down. And maybe the on the point is an ultra-compact object. The second category, the one without hidden wormholes, is much more tricky. We don't know exactly then, we don't understand yet if it has similar stability. It's of course more radical departure from standard physics. You need an high-energy condition violation, which nonetheless is violated by quantum effects like Hawking radiation, for example. So it is possible in principle that could be entailed by an effective field theory summarizing the effects of quantum gravity. And in that case, the endpoint is not clear. Maybe a naked wormhole, or maybe a long-living black hole, which when you fall inside, you will find yourself on another side of the universe. In any case, the interesting point is that via quasi-normal modes, echoes, shadows, they may be probed this alternative geometry, and maybe that in the future, if we are hopeful, in not so many decades, by shaking a black box, we will be able to guess what is the inside, and so understanding a bit better how quantum gravity works inside black holes by just looking at that. Thank you.
Thanks a lot, Stefano, for this very nice review of the status of this subject. So I guess this will be time for some questions from the audience.
Yeah, maybe I can start with some queries. Yeah.
Sure.
So, Stefano, I mean, okay, so these are very interesting solutions, but how do you see them as physical objects? I mean, do they actually are candidate of stars in the sky, or?
It depends a little bit on what I just said in the conclusion, no? Because it seems to me that the regular black hole stationary geometry that people have studied for many time now, simply now they are again more popular because we have an actual possibility to test them. This one will never be realized in nature because their inner horizon is unstable. So I don't think that they will be exactly, I mean, the stationary solution cannot be there. But you see, the problem is that why we don't apply the same standard to Kerr? I mean, the Kerr solution has an inner horizon. All the stability I talked about are there for Kerr. I mean, why we trust so much that the Kerr solution will be exactly Kerr outside? You may say, okay, because once matter cross the outer horizon, you have a uniqueness theorem. The uniqueness theorem, first of all, applies to stationary geometry. You have to add the stationarity when you have axis symmetry. And so if the geometry never gets completely stationary, it's not clear how that applied. But even apply that reasoning, think about it. If the inner horizon starts to be unstable before your outer horizon becomes null, in principle, that horizon, and this instability can also be semi-classical, so that horizon can be even time-like. the evolution of the outer horizon. So in principle, it can stabilize on something that has a tail where the Ricci scalar, the Ricci tensor, sorry, is not zero outside of the outer horizon. It's not completely, what I mean is we don't have a theorem assuring us that this is the case. We have a prejudice. So I'm not saying that this is necessarily the case, but I'm just saying that at the moment, I've never seen, a study of a collapse generating a Kerr black hole where you take into account the semi-classical instability of the inner horizon, and you basically say all is hunky-dory. And let me say, a lot of people is focused on the possibility of semi-classical effect to avoid the outer horizon formation. I think that if you have an almost free-falling collapse, that is wishful thinking. I don't see how you can do it. And I don't see how you can have a general statement that an outer horizon that may appear in a very low curvature gravity region could be avoided. But the inner horizon instability is always there. And you see here you have this focusing is really a very different form. You can say that the outer horizon is metastable due to Hawking radiation, but it's a very different thing what is happening at the inner horizon. So I think that my message is let's start to think not in terms of event horizon and Cauchy horizon. Let's think in terms of future outer trapping horizon, future outer inner trapping horizon. Let's take into account the dynamics of this object, and let's try to understand classical and semi-classical effects when you have dynamical trapped region, because those are physics, not the stationary black hole.
So this interesting solution which you have shown that kappa minus is 0, but kappa plus is not 0. That solution is for a particular theory, or is it constructed just by hand?
No, it's constructed by hand. It's constructed by hand. It's just a proof of principle that you can get solution, you can build solution which have multiply degenerate horizons. And this multiply degenerate horizon would be a possibility to have, you see, because if you have, for example, a multiply degenerate horizon inside a Kerr black hole, you can still have that there is no mass inflation because kappa minus is 0, but you don't need to have the Kerr black hole to be maximally rotating. You break the link between extremality of the, because the outer horizon is not extremal. So you may have a black hole that in the sky are not maximally rotating, they're not extremal, but at the same time, they may have this multiply degenerate inner horizon. The problem is that at the moment, there is no back reaction calculation of the inner horizon that proves that this is an attractor in some case.
Okay, thanks. That's
any other questions from the audience?
May I ask a question?
Yeah, please.
So my question is that in this solution, for example, the one with the zero surface gravity at the inner horizon. So as you said that this solution was constructed by hand, but there was subsequently a paper which I think you also highlighted where they studied the semi-classical instability of the inner horizon and said that there was a semi-classical instability. Now, for studying a semi-classical instability, we need the field equations. If this solution is constructed by hand, then how can we actually study instability using the Einstein's field equations?
Because you can always think that this is a solution that you can insert in the Einstein field equation and have an effective stress energy tensor that would be non-zero, of course. It's not a vacuum solution of general relativity, but of course you can always find a stress energy tensor of which this is a solution, for which this is a solution of general relativity. So the people that was really looking at the semi-classical instability, so making basically the point that having a zero inner horizon surface gravity is not enough because basically you still have that this being zero doesn't solve the issue. We're considering the solution to be a solution of GR with a non-zero stress energy tensor. Now, how much does it make sense? I mean, this is true for all the regular Polycode solution. People generically was thinking that this effective stress energy tensor that you find is not real matter, but is what you would call the net effect of your effective action. So you can always think of the effective action coming from quantum gravity as Einstein-Hilbert plus stuff. When you calculate the action, the equation of motion on a given solution, what you're doing is that the effective stress energy tensor would be the byproduct of these extra terms which are coming in your effective field theory. So that is the logic. Of course, it's not what let me say, we have to do more. I'm not saying that this is enough to stop here. But you see, the problem in a certain sense is that the analysis I did at the start, the local analysis, doesn't rely at all on the field equation, right? It's just telling you what are the ways you can get the focusing. Now, the solution that are embodying the local resolution of the focusing are completely arbitrary. That you can build many regular black hole solution by hand, and you can have many effective stress energy tensors. So you need a guidance from some more, justified theory that tells you. This is why, for example, I was stressing that recently in 4D it was found that, for example, in this paper by Econ and Fernandez, they find that in a theory that they have some way to justify as a regularization of f of Vargas Bonnet, you get basically in 4D a theory that produces the High-Ward solution. Again, this is not yet the end of the story, of course. It's just the start.
And so my second question was actually related to this paper, Bueno et al. So can you just tell us something about it? Because if I remember correctly, they were saying that they could construct regular black holes in 5D in pure gravity, that is without assuming there is any exotic matter.
Yeah, they find vacuum solution of a particular set of theory. These are theory constructed in such a way that, I don't know, in 5D, when you specialize your metric element to be spherically symmetric, they give you only second order field equation. So they do not have the problem of higher, if you go to higher dimension, you add the higher curvature terms, generically, you have a ghost and stuff like that, no? So basically, these are theories that are tuned in such a way that the terms that are allowed are the one that when you specialize to spherical symmetric metric gives you a second order field equation. And you can show that the vacuum solution of this theory could be regular black holes of the type 1.
So I suppose that extending these solutions to rotating cases are not straightforward.
I think now my memory fails. I don't remember if they've done it or I talked with Bueno and they was telling me that they are going to do it. But you see, most of the interest is not so much in going for rotation, but in going for d equal 4. The problem is that so far it works only for d greater than 4.
Yes, right. Okay, thank you.
Well, you're welcome.
Any other question from the audience? Okay, so if not, then let us thank Stefano once again for this very nice talk, and maybe we close the session.
Thank you, Stefano.
Yeah, yeah.
Thank you for coming.
Yeah, and thanks to all for joining.
Bye.
Bye, everybody. Yeah.
Bye.
So we are ending the session.